Welcome to Manish Kumar channel. So today we are going to talk about the span of a vector space over the real field. Okay. So what we are going to discuss in this lecture today, concept of span, and then we will see how linear combination is related to it, and then more importantly, linear dependence. That is, in other words, we call it as redundancy. And if a vector can be written as a linear combination of others, that means it is redundant in the span, right? It means it is not providing any extra information to the span, right? And then understanding span helps in eliminating unnecessary dimension, and that is very useful in data compression and optimization. These are the real life example where a span can help a very drastic role. So what is the definition of span? So if you see, given a set yes, you can think of like you have a vector space V over real line R, and if you have vector V1, V2, V3, and so on, so you take some collections, right? Similarly here, if you see, yes is a subset of a vector space V and having V1, V2, Vn elements of the vector space, then their span is the linear combination of these vectors. Linear combination alpha 1 V1 plus alpha 2 V2 and so on, where each alpha I belongs to the field, right? It means that the span is the set of all linear combination of the given vectors, right? If I say span S is only V2, V3 as per the picture, then linear so span S is the V3, V2, V2, V3, then span will be span of S will be the linear combination of V2 alpha 2 plus alpha 3 V3 such that alpha 1, alpha 2 and alpha 3 belongs to R, right? So all linear combinations. Okay. Now let us see some key properties. So span is a subspace containing S. Span is the smallest subspace of V containing S, right? How can you justify span of S is the intersection of all subspaces containing S. So if you take S is the span of a set S of a vector space V. So if you take W is a subspace of V, right? Such that W contains S, okay? Then you collect all such subspaces, and then when you take intersection, which will become span of S, right? So how can we see if you have, let's say, one space V, and if you say this is my W, and this is, you can say, my span of any set yes, and this is, you can say, this is your set yes. So if you see, yes is contained in W, right, clearly, and W is a subspace of V, right? Then intersection of is then span is the intersection of all subspaces, right? So if you see S, span S is the smaller than this, right? If I say for a moment, let's say if I give you this structure, right, which is V, and if I say this is my W and this is my S, this is W, this is S, this is S, and span S, this is span S, and this is my tiny set is yes, right? So yes contains W, right? And W is a subspace of V, but this case does not arise because if you take intersection, span is outside of the W. right? So this case does not hold. So this is not at all the case actually, I want to say, right? So this will happen always. Okay. Similarly, span of S is equal to the set itself if and only if S is a subspace. Okay. And span of S is span S itself. Another key properties, if S has finite number of vectors, and then you can say that span of V1, V2 is nothing but the span of uh, V1, V2 and difference of V1, V2, right? So this you can make correction V1. Okay. And if alpha 1, alpha 2 and so on alpha and all non-zero scalars, then span of the vectors is equal to the alpha 1 V1 span, alpha 2 V3 and alpha and Vn, the span will be the same, right? Now suppose any element Vk from the span belongs to span, what does it mean? Vk can be written as the linear combination of remaining vectors, right? It means that Vk is dependent in this set. If Vk is dependent, then it is not giving any extra information to the space or neither producing any new direction or independent. So this vector is dependent. So we can throw away this Vk from the set, then remaining set will span the entire set, right? So entire space. So span of V1, V2, Vn is nothing but the span of V1, V2, Vk minus 1 and remaining vectors, because Vk was the vector which is dependent on the preceding vector, right? Vk. So that's what Vk was removed from the space, right? From the span. More generally, if any Vk is a linear combination of other vectors, then span of this vector is nothing but the same, right? And if S is empty set, then span will be the singleton zero vector, right? Theorem, span is a subspace. So let us prove how the span is going to be a subspace. If S is the set of vectors in V, then span of S is a subspace. The proof is clearly very simple because 0 belongs to the S, 0 vector, and as S is closed, S should be closed under addition and S should be closed under multiplication. This is the three criteria, or two criteria we can say, to prove the given space is a subspace, right? So this two is also enough to show, right? V1, V2 is in span, then their linear combination as well, then vector addition as well, and similarly the linear combination will also be in the span. So this is the proof, very simple proof, right? Subspace we have to prove. Then we will see the span of two vectors in R2. So if you see span 1 0 0 1, so span is nothing but the linear combination of these two vectors, and this will generate entire R2, right? Another example, uh, so if you see these vectors are Li actually, linearly independent. Okay, these two vector, because you cannot generate the quantity 1 here with the help of 0. If you anytime if you multiply with 0 1, no matter how much alpha you take, this first tuple will remain 0 always, right? So first tuple you cannot make as non-zero, right? 1. So it means this cannot be written as a linear combination of V2, cannot be written as a linear combination of V1. Similarly, the second tuple of the V2 cannot be generated by the help of V1. Therefore, this is Li, linearly independent. Okay, and this will somehow indicate as the, we are trying to, you have vector space V, we are trying to see how the basis can be constructed for the vector space if we are having, if any set of vectors are spanning whole vector space V. That means every element can be written as the span element, written as a linear combination of a span element, right? So we are trying to see what is the minimum set which can basically generate whole space. So that is lead to the direction of basis. Okay, so we will see how the basis can be defined and all. Okay, so this is actually basis for your R2 1001, and this is known as standard basis. We will see later. Linearly dependent vectors in R2. So if you see this and this, if I see the picture, if I draw the picture, right, and then if I say 1 2, 1 x-axis, 2 y-axis. So 1 2 means this point. So if I get add, this is a one vector, and if I do in the another direction, so this is the next vector, right? So what had happened is this is a 1 2 first vector v1, and this is v2. So you see here in the same direction, right? This is in the same direction. Okay, so if I can say v1 can be written as 1 by 2 times v2, right? It means that I can find alpha which is non-zero such that I can write v1 in terms of v2. So it means that this V2 is not giving any extra information. Extra information I mean to say is not giving any new direction, right? Same direction it is. So it can generate the line, right? So your U1 is V1 is itself capable to generate the line, right? You got my point or not? And line is a subspace of your R2. It cannot generate entire space, right? Space R2. So V2 is dependent basically, right? So we can throw out V2 from this, so it can be span of V1 I can say, or else span of V2 you can say, right? So anywhere you can think of, because this is an extra information, redundant information is being given. So this is linearly dependent vectors, okay? Cannot generate whole R2. Similarly, span of R3 vectors, so you can see clearly none of them can be generated by others. So span will be whole, spanning whole space R3, right? Entire vector space can be generated, and this is called standard basis, right? And if you see V1 and V2, then span consist of this will also generate R3. So if you see in this example, previous example, right? If you see the picture where we have made this one, right? If I can give you another set v1 as 1 comma 0, right? So what does this picture says? 1 comma 0 will be here, right? v2 if I give you 2 comma 0, what you will get in the same direction, right? So you are giving me v1 v2 in the same direction. So v2 is not giving any extra information, right? You got important or not? So this can also generate the line. Okay. If I can give you a vector which is different from this direction, right? V1 is this, and if I say, let's say V2 is this, right? Rather than this, then what I can say, then I can use the parallelogram law to generate new V3, V4, and so on, and then entire space can be generated. So since span is not unique, right? Then we can also claim later basis is not unique, right? Any vector space can have more than one basis, right? Because of this span criteria. Okay. And then non-spanning set, it's not going to span again the similar, because they are linearly dependent, cannot span entire R3. So this is very important method for simplifying span, or using row reduced echelon form, or row reduction, RREF, or sometimes we call it as simplified span method. So what exactly we are trying to do? We are trying to find the span for from the given set, and we will see whether it can generate entire vector space or not. And once span is being received in our hand, we can tell that whether some vector belongs to the space or not, or something like that, right? So we are trying to construct basically the basis. Later we will see how. So suppose S is a finite subset of Rn consisting of k vectors, k greater than or equal to 2, then form a matrix k cross n using the vectors of S as the rows of A. Okay, whatever vectors are given, you can just write in the rows of A. And then span is the row space of A, right? And then reduce this. Let's suppose C is reduced after RREF. A, apply RREF, get matrix C. So once C is reduced row echelon form of matrix A, then simplified form of span is given by the set of all linear combination of the non-zero vectors of rows of C. So whatever the non-zero rows you are going to get, you take the linear combination and simplify it. That will be the span of the given set. Okay. So let us see one example. Sometimes we call it as shrinking span using RREF, right? So let us say we have three vectors, right? And we are going to have R4 basically, right? So three vector, as you see, as you have seen, minimum vector required to generate R4 is four vectors. So definitely this is not going to span entire R4, right? Because R4 required four linearly independent vectors to generate, as similar to R2. So construct the matrix. What's the construction? It says every vector can be assigned in the rows. So this will be row 1, this will be row 2, and this will be row 3 of the matrix A. So R1, R2, R3. Now use reduced row echelon form, RREF, or Gauss-Jordan we used to say sometime, and then apply. So this is 2 times, if you do R2 minus 2 times of R1, and R3 minus 3 times of R1. This is the elementary operation I'm going to use. So once you use, you will get this result. So along the pivot, all zeros, then pivot above below both zeros. To get zeros, you have to subtract R3. Uh, you can say R1, subtract R2 from R1, right? So you can say R1 and R2 you have to subtract in this step. So you will get after applying this, you will get the final step. So this is basically your reduced matrix, right? So two times you have to do. Two times you have to do, because if you multiply two times and subtract from R1 in the previous step, so you'll get finally this matrix. Okay. So now if you see the linear combination, the span will be the linear combination of the row vectors. So row vectors, just as it is, you write and multiply alpha times. So what you are going to get? You are going to get, this is a simplified span where alpha 1, alpha 2 are the scalars, is a subspace of R4, right? Now you see here, the vectors are, which has no pivot element, are free vector, right? Free vector. Therefore, you cannot generate entire R4. So if I give you 2 and let's say 7 and then 7 and then 8, does it belongs to the span of yes? Answer is no. Why? You see, first tuple is alpha, alpha is 2. So second tuple is anything, alpha 2 is arbitrarily you can take from real line. Alpha 2 is 7, let's say. Now third tuple says I am totally dependent on the first tuple and is exactly by 3 times. So 2 into 3, 6 should come, but we have written 7. So it does not belong to the span. Similarly, second last tuple says I am the exactly the 4 times of this. So if I replace 7 by 6, then it belongs to span. If I don't write 6 and say 7, then it does not belongs to span. So this is how we can check any vector is in span or not. Okay. And then one more theorem, equality of a span. S is a collection of vectors v1, v2, vn, and r, and S dash is another span, is another set v1, v2, w1, w2, wk. Then these two sets of vectors are from vector space V. Then span of S is equal to span of S dash if and only if, reverse condition is also true, right? If and only if each vector in S is a linear combination of those in S dash, and each vectors of S dash is a linear combination of those in S. So vice versa. Okay, how do we prove this? So let us prove it. So proof, okay, so let us see the proof of theorem 1. So if each vector S is a linear combination of those in S dash, then we can say that S span of S contained in S dash. Because if you know, if I want to prove A equal to B, and if then I have to say A is contained in B and B is contained in A, then I can say that A is equal to B. How do I say? If I say any X belongs to A, also belongs to X belongs to B, then we will say A is contained in B, right? And similarly we can prove. So this is the logic here we are going to use. So linear combinations of S, so span of S contained in S dash. Similarly, linear combination of S dash, those in S, so a span of S dash contained in S. So this is how span of S equal to S dash. Assume for some time being, if any one of the vector cannot be written as the linear combination of the vectors of S dash, then all possible alpha 1, alpha 2, alpha n are coming from the field. Then V is in a span, but Vi is not in the span of Vs dash, right? Therefore, span of S is not equal to span of S dash, and vice versa, right? This way we can prove. Okay. So thank you very much. Thanks a lot.